Right. So as Zay just mentioned, I want to talk today about some recent work that we've been doing in the NLP group on trying to come up with a method to get some scalable eye movement data, kind of like at the scale that we can use for these like computational applications. And basically, I want to talk about our motivations and why we're interested in doing this in the first place. And what we have right now is we've completed a pilot study. And so I want to just kind of explain what we've done, look at the results, and then the next steps are still at this point very open-ended. So we're considering a lot of things. We actually conceived this project like around the time that like ChatGPT came out, which of course like changed the landscape quite a bit. So we're definitely like pivoting from where we first were when starting this project. Anyway, so looking forward to hearing any thoughts y'all have. Please interrupt me at any time as I'm speaking as well. I'm more than happy to talk about things as we go. All right. So the idea behind why we're interested in getting some eye movement data for NLP is basically coming from the fact that our NLP systems always need to be learning in some way from humans, even if it's just like, from the text that humans have written down over the years. And a lot of times, a really valuable tool for doing this is human annotations. And so, for example, a very popular and relatively new annotation scheme right now is this kind of like human preference data, which is popularized from the release of ChatGPT. So OpenAI kind of perfected this pipeline. And how it works is you basically have like a couple of documents, a couple of like pieces of text. And then you bring in, some human annotators, and you ask them like which text they like better, and the human answers. And you use this information to develop NLP systems that are going to be creating this like better text, right? And better can mean a lot of things. So we can ask people like, which text is a better answer to some question, or like, which text is sadder or funnier or more helpful or anything else that you could think of. Okay, so this is the kind of annotations that we usually have for NLP systems. And this is something that we can kind of construe to be some sort of like self-report data, where, we're asking people to share with us their thoughts in some form about which text is better, or there are a bunch of other, questions that we might ask people. So the idea here for bringing in eye movement data is that it's nice to supplement our self-report data with some kind of like behavioral data. So we can see like not only what people's impressions are of the text when we ask them, but we can also get an idea of like, how are they actually reading the text? Is there a part that they keep going back to? Is there a part that causes them to, like backtrack a lot because it's really confusing? How long does it take them to read certain parts? All kinds of small details from the reading process that we can't get access to from just the self-report data. And the idea in incorporating both of these things is that, for one thing, if we don't have this kind of behavioral data, our models have no sense of like what the reading process actually looks like. So, formatting information, for example, to like minimize eye movements is like not something that a model can do just from like that easily just from self-report data. It's much better to have some model of like how people's eyes are actually moving over the text. And there's also this idea that kind of by incorporating like these two perspectives on text, we can actually improve the performance for NLP systems on a variety of tasks, such as like things like text classification and things like that. This task performance idea, of course, like doesn't really apply to the most state-of-the-art models now. So the recent generation like GPT-4 and things like that. But it is particularly helpful in low resource settings. So basically, if we have a model that's not quite so beefy as GPT-4, or maybe we have a language that doesn't have as much data as something like English, these kinds of eye movement data can be helpful for task performance improvements. All right, and then the final motivation is that another thing that we might be interested in NLP research is a more theoretical question, which is kind of like how close is the model processing, so like the internals of the model, how close is it to the internals of like the human processing system? So we can kind of like introspect with our NLP models and figure out like what tokens they're paying the most attention to when they're processing the text, and we can compare this with our eye movement data to see kind of like what words are drawing the most attention for the reader, and see how much overlap there is, and use this as kind of a measure of like how cognitively plausible a model is. Okay, so there is there's been some sustained small interest over the last like, I don't know, 5-10 years or so on incorporating some eye movement data in NLP for these reasons. It's rare that people are actually able to collect like a new data set for use in NLP. And that's mainly just a scalability problem. So it's really difficult and expensive and time consuming to collect eye tracking data, as I'm sure some of you are familiar with. And the, data sets that we want to use for our NLP systems are going to be like, oftentimes like hundreds of thousands of items. So this is going to be like very, very difficult for us to do with like a traditional like in-person eye tracking study. So for this pilot study that we're doing, we want to investigate a way that we can potentially collect eye tracking data without actually having to bring people in the lab and, use an eye tracking machine to capture their data. So our inspiration for this, for our experimental setup is kind of just comes from a self-paced reading task. So again, I'm sure most people here are like more familiar with this task than I am. But the basic idea, right, is that you can mask, you can have a text and you can mask it. And then you reveal like a word or phrase at a time, and the user can press a button on the keyboard to reveal like the next word or phrase, and so on and so forth. So this is obviously much more lightweight than eye tracking, doesn't require any special equipment. And it's obviously easily scalable because it can be, just delivered online and some platform like Mechanical Turk, where we can, easily reach a lot of people and collect their data. But we wanted to slightly adjust this task for like a couple of goals. So one concern that we had was we are interested primarily in showing people, longer texts. So like if we're going to be showing people like multiple paragraphs, this sort of like revealing like a word or phrase at a time, and like, maybe you can go backwards, but you can't go backwards that efficiently if you need to like reread something. So we wanted to create an interface that was more suited for kind of like, maybe a whole like article or story rather than just a sentence. And we also wanted to mimic a natural reading pattern a little bit more. So what we ended up deciding to do was something that we're calling, for now, spotlight reading. And the idea is that we turn the user's mouse into a sort of spotlight that reveals a section of text, and they can freely move their mouse around to read the article. So I lost my own mouse. Okay. So you can kind of see this is like what the interface looks like for people, and they can have some idea of like where they are in the text. We wanted them to be able to like even be able to see like a little bit of the line like above and below where they currently are, to make kind of like searching around a little bit easier. But also, we can have a pretty good idea of how their reading process is going by looking at like, what words are being revealed and for how long based on their mouse movement. So, all right, so we ran this experiment to get an idea of like what this data would look like. We got 90 people to complete it, and the paradigm for these kinds of like online crowdsourced studies is usually they're on the shorter side. So we wanted to limit it to about like 15 minutes for each participant. So each participant only reads about like 5 news articles. And then, they have some like rating task and like one free recall task to incentivize at least like some level of attention that they pay when they're reading these articles. And then we also had an in-person study with the same data set. So this is on a smaller scale, only 20 participants, but we keep them for longer, for about an hour. So we have them read like 20 news articles and answer like 4 of these free recall questions. And the first thing that we're really interested in from this pilot study is just seeing like to what extent the online data that we're collecting with this like spotlight reading experiment is going to be mimicking our in-person data. So like more specifically, we want to evaluate whether we can comfortably use this online data as a substitute for like our eye tracking data. So like, can we, go out and collect a massive amount of like online data and, do some further experiments with it because we can claim that it's like at least somewhat similar to a quote unquote real like eye tracking experiment. Okay. Um, so the one of the challenges for this was actually figuring out how to get these 2 data types into roughly the same form. So from the eye tracking data, we are using an iLink eye tracker with its data software that automatically can parse the data from the camera into the kinds of eye movement data that are typically analyzed in eye tracking research. So things like dwell time, fixation counts, regressions, things like that. And of course, for our spotlight reading data, this is just our program. So we have sort of the raw mouse movements, but we don't have anything else. So our basic approach to processing our online data, our goal was to get it into the same form that our eye tracking data is in. Um, so basically, we take the mouse data that we have from our experiment database. We look at the revealed character spans that correspond to each of these mouse movements. We look at like what centered word is like most visible, and we designate this as our interest area. And from there, the metrics, the eye tracking metrics that we were like comfortably able to calculate were these ones at the bottom, which is just the overall dwell time for each interest area, the fixation count within the area, which is a little bit off from the real fixation count, but those details are a little bit tedious. So I just will put a imaginary asterisk here for you all. The number of regressions out of each interest area, and also the first run dwell time for each interest area. So really these fixation count regressions, first run dwell time it's a little bit we were most confident, I guess, in the dwell time metric for being like maybe having the most high fidelity with like the kind of information that we would be getting from the eye tracker. So we focused on the dwell time data between the online experiment and the in-person experiment in order to kind of like dig a little bit deeper and see kind of like how close are both of these. So the first thing that we looked at to get a sense of the relationship between the data collected from both of these experiments is we just wanted to look at like the overall distribution, like across all of the interest areas in the experiment, just kind of like what is the overall distribution for the dwell time data. So like, are people spending like about the same amount of time reading each word in both experimental settings? And when we looked at the overall, like, so these are just kind of histograms, and we look at these probability distributions based on the frequencies of the data that we're observing. We looked at the KL divergence between the two probability distributions, which is a choice that's primarily because this is a measure that's really common within computer science to measure distance of probability distributions. So essentially we find that the distance is like pretty low. Of course, you can see that there's some clear like differences between these two. So for the eye tracking data, the peak is a little bit sharper. And the slope is a little bit more swoopy, or is it a little bit more straight here? But they're both these like very they have this like long right tail, and their distributions peak at a similar point. So this is why we have this like low KL metric between the two, but they are still they're still distinct in that way. Yes.
Um, so I have a question. So
Yeah.
when you are doing this per subject normalization,
Yeah.
I guess the on-site participants, they did both the spotlight and eye tracking.
No. So they did not do both, actually. So they're completely different people.
Okay, then what do you mean by per subject then?
So for per subject, it's basically just the per subject z-score for each person. So the idea just being that like this helps where if you have some like slower readers or faster readers, if you do the per subject normalization, then you're just looking like for each person, are they looking at this area like longer
Okay.
or not, if that makes sense.
But the material that they looked at is of course the same, right?
Yeah, it is the same, although it's not like perfectly the same in terms of like, the in-person study is longer. And so we have like more, basically we have more data for the spotlight reading experiment, and yeah.
And also one more question is the dwell time zone. Are they like are the words matched?
Are the words matched like for this like distribution?
Yeah, because
specifically. Yeah, so we also look at the correlation for like each individual like interest area. But this is not looking at like, okay, so maybe I'll go forward and talk about this, and then maybe your question will be answered. Yeah, so basically for this, like the question is like the question may be maybe a more like realistic motivation for like why we're looking at this is like, this spotlight reading task is very artificial, right? Like in terms of like you're kind of revealing the text like by moving your mouse. And so like maybe that's like fundamentally changing like the amount of time that it like takes people to read, right? Or maybe like it is really going to lead to like a fundamentally different reading pattern in which we would see like the dwell time data looking like, just if you look at just the distribution overall of dwell times, like how long people are spending on words on average, like maybe that looks very different if the experiment is too weird, was our concern. Okay, so then we also wanted to see though if there is a correlation like for each of these words, if there's a correlation between how long people are spending on each word relative to the rest of the text across the two experiments. So basically, like if there's an interest area where people have like long dwell times in the eye tracking experiment, we would also want them to have long dwell times in the spotlight reading experiment, right? So this is a density heat map where, sorry, I didn't get a chance to fix these axis labels to make it clearer, but basically this is a density heat map of the eye tracking on the y-axis and the spotlight reading on the x-axis. And so basically if this was a really good correlation, we would see a really nice, straight diagonal line. And we see that there is some correlation trend here in this data. And if we do Pearson's R, we get a correlation coefficient of like 0.3. It is statistically significant, but it's not necessarily like it's not like, yeah, the highest correlation value we could have, but it does seem like there's at least some correspondence between the two experiment modes in terms of which words are being focused on like more or less. Okay, so our conclusion from looking at this dwell time data across these two experimental modes is like, at least for our purposes, we feel that the spotlight reading dwell times are a reasonable approximation for our eye tracking dwell times. And our hope is that we can more demonstrate this through some kind of like downstream task effectiveness. So basically we wanted to just check for ourselves, like if we feel comfortable like going out and collecting a bunch more of this data, like does it seem useful enough to collect more of it? And we feel like at this stage, it is worth collecting more data and seeing how far we can get with it. All right. So the other thing that we are looking at in this pilot study is kind of based on the data set that we were using. So the data set that we had people read, and we'll look at some examples in a moment, has different types of errors present in the text. And so we wanted to see if different types of textual errors are affecting people's reading patterns. And these are specifically errors for machine-generated text. Again, this is an experiment that is conceived like just as ChatGPT is coming out, that doesn't quite have the errors to the same degree. But anyway, so the this is an example of the kind of news articles that are in this data set. This is one that is written by the GPT-3 model. And this is a data set that is from Dow et al. In 2022, where they also have annotators like read through these computer-generated texts and annotate different types of errors that they're seeing. So I think there's about like 10 error types. I'm going to go through some of them one by one and look at like kind of our what our data shows for each of these error types. Um, One issue is that they have 10 annotators. They rate error severity on a scale of 1 to 3, and there's like a relatively low inter-annotator agreement. So for when we're looking at like, are the eye movements changing between the text with error and without error? The way we decide whether or not there's an error is basically just if more than half of the annotators have rated it as like some level of severity. This is like not necessarily ideal, so I just kind of want to point this out, that it is a kind of a bit of a difficult problem still to say maybe with confidence which portions of the text actually have these errors. All right. So first error type that I'll show some data for is redundancy. So this is the dataset's description of the redundant type of error. Is basically just text that is repeating itself. And then over here on the right side is an example. So they then made decisions based on Kondo's instructions to the extent that they created decluttered spaces and got rid of clutter and clutter-filled spaces. So it kind of gets stuck on like this clutter word, and the text becomes a little bit redundant feeling. All right. So if we look at our interest areas that we mark as like redundant versus not redundant, and what we're looking at here is just like, the average of all these interest areas and like the distance of that average from the mean. So kind of not surprisingly, this is like 0. So our not redundant interest areas, of which there are like 81,000, are pretty much just like at the mean level, which makes sense. And we see that for the redundant text points, they have, lower, basically just lower dwell time. So people don't spend so much time reading them, which makes intuitive sense. So not too surprising there, but we do kind of like to see that because it's at least a little bit of a sanity check for our data. Next type of error point that we look at is off prompt, which is another one of these error types that happens much less in the state of the art models today. So off-prompt data is basically if you have the beginning prompt for how the news article should start. So for example, if the news article should start with like China sets new record for economic growth, and the model continues by saying that the Chinese economy fell 10% this month, that is not following the prompt. So this is an example of an off-prompt error. And for these off-prompt errors, probably the most striking thing that we see is a larger amount of regressions out. So this is, again, something that we would pretty comfortably want to like predict happening, right? Where the reader encounters something that is a little bit like contradictory to the way the text started, and that's prompting our readers to go back and confirm that they didn't have the wrong idea when they run into these like off-prompt interest areas. Self-contradiction, this is really similar to off-prompt, honestly. And the only difference really is that the self-contradiction is where we have something that's contradictory, like within the text that is actually being generated by the computer. So in this case, we have like McDonald's is considering a design which will replace the cardboard packaging. And then McDonald's is saying that they're looking at a new design that minimizes the plastic bag. So first it's implied that McDonald's has cardboard packaging, and then it's implied that they have a plastic bag, which is a direct contradiction. Again, in this case, we see a really similar pattern that we saw for the off prompt, where we have a lot more regressions out when we're hitting these contradictory parts of the text.
But they don't seem to be dwelling on it much, though, right? They dwell less.
Yes, which is definitely strange. I'm not sure. I would be curious to see, like, since these are computer written texts, they can sometimes have like a lot of problems. So my personal question that I would like to see is whether part of the lower dwell time overall is because they kind of write the text off as being useless and not worth your time to try to figure out what it's saying. And that is like, yeah, that is kind of what I wonder in terms of like, and the other thing that I wonder as well is, we're only looking at the interest areas that are specifically tagged with these types of errors. So it's possible that we might see increased dwell times in like other parts of the text. For example, like you regress out of the area with the error and like back to another point. We're not tracking exactly where they're going, but those points may have maybe longer dwell times relatively, but we haven't actually looked at that yet because that's a little bit difficult to tease out.
Okay.
Yeah, but yeah, no, that is not necessarily expected that there's the lower dwell time overall. Yeah.
If the texts are already marked, then I think it makes sense. You're saying that the texts are marked with like arrows, right? Like which part they're marked.
So like not what the participants see.
Oh, okay.
Yeah. So the participants just see the text, and we also we have also some like human versions, so like the actual original human completion. We mix some of those in as well just to increase like the average quality of the articles, as well as to we were also interested in seeing if there was any pattern like overall between like the human written texts and the machine written ones. It seems like there's like lower dwell times overall for the computer written texts, but yeah.
Okay.
Yeah. So yeah, we also have these common sense errors, which are just, things that are just weird to say, such as that there are 10 or 100,000 astronauts working on the South Pole. Again, this is another kind of error that you see much less with modern models. This was a weird case because using our methodology of marking something as an error if more than like half of the annotators agreed that it was an error. We got like a really, really low number of interest areas, like only 58. And as you can see, our confidence intervals are very difficult. We just don't quite have enough data. So I think, yeah. So I tried to like kind of loosen the restriction a little bit and include also parts of the text that maybe like fewer people marked as a common sense error. And I got this result, which is just kind of like lower dwell times overall, which is also, again, as kind of as Zay was pointing out, we would have probably predicted longer dwell times for people to try to figure out like, what the heck is going on here. But again, this is a little bit of a data scarcity problem. So if we expand this out and are able to like look at a wider part of the data, we might be able to make a stronger conclusion about this area. So this is still a little bit of a question mark for me.
Yeah, we have a question.
Oh, yeah.
So are these differences from the mean the
Yes,
same as real
yes.
life?
Yeah, exactly. So this is just, sorry, I should have mentioned that for sure. So yeah, this is like looking at the difference from the mean, which is just this line here, and this is all for the online data. So for the in-person data, there's frankly just not really enough of it for us to be able to like do any kind of like this analysis on it because yeah, it's we just don't have quite enough data. So we're just looking at the online data right now.
All right, thank you.
Cool. Um, right. So only a couple more error types that I'm gonna go through. So thanks y'all for bearing with me. Next error type is like grammar usage, which is a little bit of a weird one. So the people who made this data set say that this category is for things like missing words, extra words, and incorrect or out of order words. And it's one of the ones with sometimes pretty low levels of inter-annotator agreement because it's a little bit of a grab bag category. But when we looked at these interest areas that are tagged with this grammar usage error, we find a similar pattern for a lot of these errors where we're getting a lot of regressions out for these error interest areas. And we're also getting like a little bit higher number of like fixation counts. So like people are just generally hanging out in these areas a little bit more with their mouse, even though it's not really corresponding to a higher overall dwell time. All right, I believe this is the last error type that I'm going to be talking about, which is encyclopedic. And this is a factual error. And it's to me, it's a little bit it's like not so clear that this is fundamentally a different error type here, like something like Japanese Prime Minister Justin Trudeau. Like, I'm not sure that that for me feels like a different error type than something like 100,000 astronauts on the South Pole. But that is how this data set is defined. So we're sticking with their error definitions for now. Interestingly, for these encyclopedic errors, this is the only error category where we do find like longer overall dwell times. And this is also something with a really low number of interest areas, though, where people are agreeing. So this might be kind of influencing this outcome as well. But this is definitely something that we're going to be keeping an eye out for in the future. All right. So basically, overall, from looking at this data and thinking about this research question of like, do we have some like distinct reading patterns for different types of errors in text? And it seems like there may be some patterns developing based on the data that we've collected so far. In particular, we tend to notice like lower dwell times. Again, I'm not sure how much of that is just related to the computer text, like just not being so not being like as worth reading in a sense for people. Anyway, we're also seeing a lot more regressions out for many errors, but again, it's difficult to draw some strong conclusions because of what I was mentioning with having this low inter-annotator agreement. And it's also not clear that these error categorizations are like necessarily how we would want them defined for like our specific purposes. And there are also absolutely cases in which, even more data, so collecting like data for an even larger swath of this data set would be helpful for us. All right, so that's the main part of the pilot study, that the results that I wanted to share with you all. And then we were really just hoping to talk a little bit about sort of what we might want to do next, using this kind of experimental paradigm to hopefully collect like a large amount of reading data. And the main thing that we're seeing in the NLP literature over like the last year, for reading data is focused around predicting a scan path. And I would actually be interested to hear if this is something that appears in like in other fields outside of NLP, because yeah, I wasn't sure if this was something that that researchers on the NLP side of things had been thinking of, or if this is inspired from like other areas. But anyway, the idea for the scan path is it's a data structure that basically just stores like fixation data for a text. So it's going to be a set of pairs of like words and durations. And this is going to be ordered such that like, the first element is the first fixation that the reader had, and the last element is the last fixation. So you can have words repeating multiple times within this scan path. And from this scan path, you implicitly have information such as like, the total dwell time for each word. You also have implicit information about regressions because of like the ordering of the words and things like that. So anyway, so this is an area that is of interest in NLP research right now, is using reading data from people to develop models that can predict for a given piece of text, like what is a realistic scan path that somebody might have as they're reading it. And again, this is something that has shown some promise, particularly for like low resource type settings or like data scarce settings. So if you are incorporating the scan path data into your NLP pipeline, you can get stronger performance if you're limited to like, let's just say like 200 to like 400 examples, instead of like the thousands, tens of thousands that we would normally like to see for an NLP application. Yeah, I guess this is, I probably should have gone to this a little bit earlier. This is just a visualization that we have to look at scan paths. So for a given text, you have like this almost like time series data of like exactly how people are moving from word to word, as well as this like duration data in terms of how long or short a person is spending on each word. So yeah, we've been brainstorming like a few different things that we might want to do with this. But one of the questions that we had for people in this group actually is just sort of about this like scan path data in general, because we were wondering if if a model that can generate these sorts of scan paths, like we were wondering if it can be useful for other fields that are concerned with text, like outside of NLP specifically. If there's like any sort of like application or like potential like use that comes to mind for you all, like if we can imagine that we have some model that can generate perfect scan paths or something for text. Like, we were interested to see if anything came to mind from this group about like something that might be useful for outside of just, as I said, for NLP task improvement or something like that. But yeah, so for us, some of the things that we were thinking of is, being able to like collect a bunch of like task specific reading data. So if we can, look at how people's reading patterns might be affected by like what their goal is when they're reading. So if you're reading text for pleasure versus for information versus other settings. We're also maybe interested in seeing if we can like personalize these a little bit more. So right now, the paradigm is basically generating a scan path that looks like it could have come from like a person rather than from a specific person. So basically, we would be interested in seeing if we can, provide some utility to specific readers, or maybe for their specific task or something like that, in order to have like a more personalized experience. And we're also kind of toying around with the idea of if scan paths could help us with some sort of like eye movement goal-oriented text generation. So perhaps we can try to a create a system that generates text such that the numbers of regressions are minimized or something like that. We're not sure if that would necessarily be like a great goal for generating text or not, or if there's some other goal for generating text based on eye movements, if that even makes sense. So that's another thing that we would be super interested to to hear thoughts on. Or even just, yeah, what kind of tasks might be interesting, or just kind of honestly just anything. We're really we're really open at this stage to figuring out where we want to go like next with this project. So anyway, thank you for listening. I think that's about all I have. Yeah.
Yeah, thank you. Thanks for the presentation. Any comments, feedbacks? Okay.
Hello?
Are you gonna are saying something, Vijay? I think you're muted or something.
Is it working now?
Yeah, we can hear you. Yeah.
Yes. I was curious if like these scan paths, at least the number of regressions that are predicted by the scan paths, track with any kind of difficulty metric for reading. I specifically am interested in like how people read code, and it would be interesting if like I can see code where like many variables refer to other variables instead of just having the direct value, whether that would correlate with the difficulty of reading metrics.
Yeah. I don't know that I've seen that looked at explicitly for the scan paths, but I wouldn't be surprised, certainly. Yeah. I wonder too, like even for code, I think some of the idea of just like the layout is also interesting there, right? In terms of like you don't necessarily want to be wasting a lot of time like searching for references that are like a long distance away, like physically. Yeah.
One interest domain would be like similar to coding, like education domain.
Yeah.
So like how, I don't know, ESL students
Yes.
look at text or something like that.
Yes. Yeah, I'm very interested in the like language learning angle that you could have with with being able to model for like specific stages of language learning, or maybe even for a specific language learner, how their eye movement is doing. And either, I'm not sure if like generating text according to this is best, or even just like modeling it as like a sense of like progress as well. So, you know, if you don't need that many samples in order to like model a person's like reading pattern, you can maybe look at how their reading ability is like improving. But yeah, the second language learning is like not an area that I know anything about really.
I was curious if you have an idea of how accurate these scan path prediction models are.
Yeah, it's really difficult, right? It's really difficult to measure exactly how accurate they are, right? Because of the wide variety in like potentially valid scan path, right? So like the only like real like gold standard ground truth would be to, I don't know, find some readers and see if anybody also produces the scan path that's like predicted, right? Basically, I think their way of evaluating the goodness of the scan paths is they'll have like some data from a couple of readers who actually like read the text, and then they'll look at things like the edit distance between the two scan paths, so like how many operations you would have to make the scan paths identical. And yeah, I think it obviously is not perfect. So I think it's very difficult to say exactly how exactly how accurate they are.
But the model must be trained on some kind of probably edit distance, right? Like, does the loss actually get to a point where it's plateaued, or does it just
Yes.
keep reducing?
Yes. Yeah,
It
so
does.
the
Okay.
training is like tractable in that way, in terms of they're able to minimize the loss function. Yeah.
That's cool. Thank you.
Yeah.
I have a couple of random-ish thoughts.
Awesome.
Within psychology, people who study comprehension, one of the places where they've paid a lot of attention to kind of scan patterns and things like that is in dealing with ambiguities. Structurally ambiguous sentences, or even ambiguous words. And there's some really interesting interactions between that and reading skill. So it's almost like skilled readers will encounter an ambiguity and they're able to keep both interpretations in mind, and so they don't regress when the ambiguity is finally resolved. But less skilled readers do have to regress. So if you're interested in skill levels and individual differences and things like that, that might be something to look at. And the other randomish thought I had was about a different paradigm altogether that might be a much richer
Oh, sure.
source of information, though I will acknowledge up front it's a pain in the ass.
Oh, no. Okay.
I think Andy knows exactly where I'm going, right, Andy? Are you familiar with the think aloud protocols?
Yes, yes.
That, I mean, they not only let you know what a reader is thinking about, but of what part of a text they're thinking about, what they're thinking about it. So you just basically have people read a text one sentence at a time and then articulate whatever is on their mind before they go on to the next sentence. And it is really a rich source of information that I think would give you a lot more insight into the moment-to-moment processing of a text that goes on inside people's heads. And so if that's what you're interested in, I would encourage you to look at that. Where it becomes a pain in the ass is having to take recordings and transcribe them. I mean, a lot of that can be done automatically now, but yeah, and I mean, I mean, it's an idea that's been around since I think the early 80s. There was a classic Psych Review article by Anders Ericsson and Herb Simon. I'm sure you know Herb Simon. I mean, one of the fathers of founding fathers of AI. But they talked about that they had this article where they talked about the conditions under which asking people to think aloud can give you useful information. And one of the things that they emphasize is you can only ask people to tell you, not to try to theorize about anything, just tell you what they're thinking while they're thinking it. And another thing they emphasize is that you have to make sure that doing that doesn't interfere with the primary task. And when it comes to comprehension, it turns out it works really well. And not only does it not interfere with comprehension, it actually improves it. And in fact, educators are using it a lot to try to, as an intervention to try to improve reading skills. So anyway, I just wanted to toss that out there as something that if you continue this line of interest, you might want to look at.
Yeah, do they have like so I think one of the challenges is like for me, I always think of this data as very like very qualitative from this sort of study. Is there any like quantitative metrics that people tend to pull from this sort of paradigm?
Andy, you're nodding your head. Did you have something specific in mind?
Yes, so you have to define in advance what you're going to be looking for from the protocols. So are you going to be looking for paraphrases? Are you going to be looking for inferences? If inferences, what kind of inferences? Elaborative inferences, textual inferences where they're connecting to a prior text, metacognitive comments. I have no idea what's going on. I got a lot of those, and but it's really useful to know that.
Yeah, no, right. Definitely, definitely. Yeah, that makes
Emotional
really
reactions. I love this, I hate this. So you have to define those. I would like to imagine that all you computer science people would have ways of developing. So in psychology, it's just inter-rater reliability. You train people. I would like to believe that there is a way of coming up with computer-based paradigms for what gets to define an elaborative inference that would allow this to be more number-based. But yes, you do indeed end up with quantitative information based on defining the categories of what you're expecting to find. There's a lot of work out there defining the categories. You
yeah,
don't have that from the ground up.
Yeah, yeah. The thing that's kind of interesting about that too is just as I said, like when we started this kind of like brainstorming for this project, it was right as the latest and greatest generation of language models were coming out. So kind of like the aspects of computer generated text, the characteristics have changed a lot, right? So like when we were first talking about this, you know, there are things like a lot of like grammar and usage errors or like super like obvious like common sense errors. And, you know, now it's much more like this kind of like canned quality of the writing or like, you know, maybe as Zay's been looking at kind of like a really consistent, like oddly consistent like discourse structure or something like that. So yeah, maybe the kind of yeah, maybe that kind of paradigm can capture those qualities much better than like reading patterns could.
I was also wondering, I mean, this is a little bit of an aside about using human think aloud protocols during reading as a data source for training language models to think like people as they're reading.
Yeah, no, because that's kind of like that's like that other that's like that second part of the motivation, right? Is like, you know, can we have kind of like
yeah, that's what I thought.
like, yeah, developing like some kind of like theory of mind for like how is the reader going to be experiencing this text? And yeah, it's a little bit of like a higher level
Mm.
than I'd originally been thinking about. But yeah, no, because there are things too with like where you're writing, right? You're supposed to like have some sort of like, you know, maybe you have some sort of hook because you expect like the reader will be really excited here, or like, you know, you can plan an elaboration because the reader is going to be confused and wants to know more or something like this.
Yeah, so
One last randomish thought that I had as I was listening to you had to do with one particular kind of data that you were looking at, and that is the fixation times.
Yeah.
So how much time do people spend looking at each word? And there's a lot of really uninteresting low-level stuff that
Yeah,
go
yeah,
into
yeah.
that. Things like word frequency and word length.
Yeah.
And psychologists who study comprehension really aren't interested in that. They're interested in deviations from that, in trying to predict where people are going to spend more time and attention beyond what's predictable just from that stuff.
Yeah.
And so personally, I think it would be more interesting to put that information into your data set than just the raw.
Yeah,
Fixation
that
times.
is so yeah, we want to that's like what we're interested in as well, obviously. But yeah, we haven't figured out like the best way to model that so far with like yeah, with what we have, which is primarily from like lack of time spent on it, to be quite honest. So
But I mean, word length is easy.
yeah,
And
yeah,
there are databases where you can easily look up word frequencies and see, if nothing else, you can just, statistically remove the effects of those variables.
yeah,
Mm.
it's on our list for sure.
Cool. Well, thanks all for the comments and insights. I'm particularly working on one of the project I'm working on is trying to teach language model to stop and plan ahead the generations that they're gonna generate, and so we're trying to sort of language model to decide whether to spit out words by words, or trying to like plan ahead like kind of the tone of the text or the discourse of the text. And I think as Randy mentioned, the Think Aloud protocol data set, if we get our hands on it, could be a useful resource, I think. Yeah. It's very interesting.
All right.
Cool.
Yeah, I think we have to
I think we're just on time. Thank you so
Thank
much.
you.
Yep. I'll share the recording as well. Yeah.
Thank you.
Thank you.